Hello everyone, this is Practical Organic Chemistry lecture course Chem 21-25, and this week's lecture talks about synthesis of hexaphenylbenzene. So throughout the previous weeks in this lesson we have seen synthesis of several organic compounds, and the pathway is an interesting reaction because every step has its own chemical procedures, and as well each of the products from a given step were reactants in the second step, and which kind of make it very interesting to see such a continuous pathway that takes us to a single organic compound, which is also one of the interesting features for reactions in organic chemistry. This also helps you to connect the reactions you learn in organic chemistry, or when you see a piece of reaction in organic chemistry, you'll for sure see it in a different topic somewhere along the course. So the purpose of this pathway was to arrive at the final compound, hexaphenylbenzene, and throughout those 2 weeks we followed two of these pathways to arrive at the major reactants. And in this week the experiment will complete that the overall reaction for all these steps of reaction, because we have already the tetraphenyl cyclopentadienone and that of the diphenyl acetylene reagents. So the final product is synthesized involving two percyclic reactions, the cycloaddition and the cheletropic reactions. Normally percyclic reactions are reactions that have a cyclic transition state, and the major classes for these reactions include cycloaddition, electrocyclic reactions, sigmatropic reactions, and cheletropic reactions. These reactions are some of the famous reactions in organic chemistry. I'd say one of the most important reactions in organic chemistry, because they give very unbelievable products, and the reaction is also, the way the reaction occurs is also very enjoyable, which you'll see in the next slide, is that we will use arrows and to make the reaction. Normally the pi electrons are the agents for this reaction. These reactions were invented by two scientists named Hoffman and Woodward, and these scientists have got a Nobel Prize in 1965 for their work. That's why we call these reactions the Hoffman and Woodward reactions, and the rules for these reactions are also named as Woodward and Hoffman rules. So these are the examples for these percyclic reactions. Cycloaddition reaction is, for instance, a reaction between a dienophile and a diene. Basic example for this is a Diels-Alder addition, and you can see it's a a reaction between two pi systems to form a cyclic system. While in electrocyclic ring opening or ring closure for that matter, you'll see the reaction happened in a concerted cyclization of a conjugated pi system, right? And in sigmatropic reactions, normally these kind of reactions are characterized by rearrangement of atoms, or an atom or a group of atoms across the across the structure, which also results in delocalization of the pi electrons. I think the best example for this one is the Cope rearrangement. In cheirotropic extrusion, normally a pair of electron and a pi bond will be participated to give the final structure, and in many cases the product appears with two newly sigma bonds. Of course, here we do not see two newly formed sigma bonds, but we can see a newly formed pi bond. But then you can also see a pair of electrons from the carbonyl carbon are involved in the reaction. In fact, they are the one that started the reaction. You can also see delocalization of pi electrons. So for this reaction, the diphenyl acetylene will act as a dienophile, and that of the tetraphenyl cyclopentadienon will act as a diene, and the dienophile attacks the diene, and then the diene electrons will delocalizes and then hits back the dienophile, and as a result we will have a bicyclo compound with a bridged carbon. And similar to the above example, we see the carbonyl carbon in the bridged carbon undergoes delocalization of its free electrons, and then the bond, as a result, the bond in the bridged carbon delocalizes, and then the pi bond again shifts into the next adjacent sigma bond, and then the sigma bond cuts back to the carbonyl carbon, and with that it pushes the carbonyl carbon to come out as carbon monoxide, and that gives us the final product, the hexaphenylbenzene. This shows the molecular orbital theory calculation for this dialdehyde cycloaddition. You can see the reaction. Okay, so you can see the diene being attached to the dienophile. Literally, the HOMO of the diene reacts with the LUMO of the dienophile. And looking at this reaction coordinate for this reaction shows that the reaction is exothermic, giving off negative 13.1 kilocalorie. It has also an activation energy of 46.3 kilocalorie, which indicates reaction must be supported by heat if it is going to proceed. Whereas exothermic simply means a reaction is that the heat is given off at the end of the reaction. And this molecular orbital calculation shows the cheirotropic extrusion for the bridge carbon, and you can see in the reaction the rearrangement occurs between the carbonyl carbon and that of the bridge carbon, and the carbon monoxide leaves at the end of the process. Here in the beginning of the reaction, you can see yellow bonds indicated by a dotted line. That's for the bridge carbon atoms, because those bonds are under high strain and they are very weak. That's why they are not included in the molecular orbital theory calculation. And this is a reaction coordinate for the extrusion, for the cheirotropic extrusion, and comparatively it has very low activation energy that indicates this reaction can proceed at room temperature without any external heat support, while it has a negative 46.7 enthalpy, which shows that the reaction is highly exothermic, and this amount of heat will be given off at the end of the reaction. So for the experiment, we'll need a round bottom flask and a heating mantle, and after that we can start the experiment by adding 0.5 grams of tetraphenyl cyclopentadienone and 0.5 gram of diphenyl acetylene into the round bottom flask, and then the flask will be heated for 15 minutes with continuous stirring using glass rod or a spatula. The reaction needs high heat, as we have discussed in the reaction coordinate. We may heat the reaction up to 200 degrees Celsius or more than that. So after that, we have to add 10 minutes of diphenyl ether still while stirring it, and we need also to see formation of homogeneous solution during the process. And then the next step is to cool the solution to room temperature, and at this point we then will add 20 milliliters of mixture of hexanes. After that, the solution can be cooled in an ice bath, and finally we can collect the products using vacuum filtration. So this reaction needs very high temperatures, and for that we need to be very careful during the reaction. In fact, because it has cooling and heating steps during the procedures, it's a good way to clamp the round bottom flask into iron stand, because that's the safest way, not only for us, but also during the experiment we need to lower the heat at some point, and it makes it easy to move the round bottom flask if it was attached to the iron stand. Also in the procedure, there is a steering step that requires us to steer using glass rod or spatula in case we do not find a steering rod, because that's recommended. But alternatively, we can also use a clean spatula to do the steering. And the reaction should come into completion immediately after we add the diphenyl ether. However, the diphenyl ether is solid at room temperature, and the way we want it in this reaction is to act as a solvent, and before we add the diphenyl ether, we need to melt it to have a solvent form of the chemical. And we can do this in the lab also with the support of the TA. Safety issues for this experiment, and there is possibly of fire danger because of the high heat procedure involved. And specifically, when we add the diphenyl ether, we need to make sure that the flask is not too hot, otherwise the ether may evaporate, and that will, you know, in that way we can inhale it. So we don't need to add the diphenyl ether if the flask is hot, but also when adding the hexanes, the reaction, the solution should be cool to room temperature, because hexanes are very low boiling point organic solvents, and if you're adding it at even a bit warm temperature above the room temperature, they can evaporate, and if they evaporate means it will affect the reaction, as well as it's also hazardous to inhale the vapors of these chemicals. High heating and fast heating and fast cooling, both of them are not recommended in reactions, especially as they result in breaking of the glasswares. For instance, if you try to cool this flask immediately in ice baths before it's slowly cooled to a room temperature, you may have a crack in the flask, and the cooling step should be done very slowly for that matter. As usual, we'll be doing a spectroscopic characterization for our final product using IR, NMR, and UV. And that's all for this lesson, and thank you for your time.